Okay, this is about pressure, the definition of pressure. So in the ear also, you can have issues with the pressure. Uh, like when you're flying, the pressure in the cabin can be greater than the atmospheric pressure, right? That's possible. Less, actually, less than the atmospheric pressure because outside pressure is less. So that can have a problem with your eardrum. The eardrum, the, the pressure difference, if it become like that, it can rupture because you should have the same pressure inside and outside of the eardrum. It, all right. So how do you get the pressure? What is the definition of pressure? P is equal to force divided by area. Here we are given the pressure, the excess pressure, the gauge pressure, and you can calculate that resulting force. That is the question. So force is equal to pressure multiplied by the area. Just substitute, but only thing you have to remember to put the units. The pressure is given in millimeter mercury. The answers are in Newton, SI unit. So that must be converted to Newton per meter square. The conversion is already there between millimeter and that. So 226 millimeter mercury, you need to get it into Newton per meter squared. So 1 is this much, so this much will be just a simply multiplication. So now you'll get the pressure in Newton per meter squared multiplied by the area of the eardrum, which is already given in meter squared. So all you have to do is to just substitute that value. This is in meter squared. Meter squared cancel with meter squared. So you'll get the answer. Hopefully, this is the answer. If anyone has a calculator, please check. Yeah. Yeah, gauge pressures. No, no, because the force will be coming from the excess pressure. That means the gauge pressure. Because outside that eardrum, it is atmospheric pressure. Excess pressure, yeah, not the, okay. So there is, because like divers, when they go into the ocean, the pressure can be greater than what is the inside pressure. So the difference in the pressure is this 226 millimeter mercury. Right. So that's easy, right? So sometimes the question is about the eye pressure. Now this is the ear pressure. It can be anything else. Right. So let me get rid of this. Now we go to question number 9. A 10-liter container holds 0.332 moles of ideal gas at a pressure of 300 millimeter mercury. What is its temperature? Now, this is not a changing of state, right? It is not going from initial to final. It is just one state. It's a matter of applying the ideal gas law, which is in this question is giving the volume, is given the number of moles, is given the pressure. So what is missing is the temperature. The question is to find the temperature. This is given, this is given, this is given. This is the constant. Of course, if it is not seen in the question itself, it will be in the formula sheet. You don't have to memorize them, it will be there. All you have to do is to substitute and find the unknown. So this is, yeah, is asking for the temperature. Yeah, 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 yeah. Yeah, I'll come to that. Okay. So let's do the, you can, if you want, you can use the solving mode, but this is a simple algebra. You know how to make P as the subject. So it will be PV over NR. So all you have to do is a simple calculation in your calculator. But the problem is, since the temperature is in Kelvin, SI unit, everything has to be in SI unit. Okay, you have no choice there, right? So pressure is millimeter mercury. This is the conversion. It is given in the question itself. 1 millimeter mercury is that much. So you'll have to do is to multiply by 133.3. So pressure, let me substitute 300 multiplied by 133.3. So now this is the pressure in Newton per meter squared. Then volume is 1 liter. Liter is not SI unit. Meter cube is the SI unit. So you have to convert the volume to meter cube. It is given as 10 liters, so it will be 10 multiplied by 10 to the minus 3 in meter cube. Divide by N. N is 0.332, that is the SI unit for N. Multiply by R. R is 8.314. Somebody help me and tell me if you are getting this answer. The answer will be in Kelvin, not in Celsius. And the choices are given. Please remove your earplug. I don't know if you are listening to me or listening to something else. All right. Thank you. All right. It says just put in your calculator and do it. I believe you all know how to use your calculator, right? This is number 10. During inhalation, a person's diaphragm and intercostal muscles contract, expanding the chest cavity and lowering the internal air pressure below ambient. So the air flows in through the mouth and nose to the lung. Okay, these are all the biology stuff. The question is this. Suppose a person's lungs hold 1,300 milliliter of air at pressure of 1 atmosphere. If they expand their chest cavity by 450 milliliters, that means the new volume is not 1,300 milliliter, it has expanded by an amount of 450 milliliters. So the new volume will be the addition of the two, while keeping their nose and mouth closed so that no air is inhaled. What will be the air pressure in the lungs in atmosphere? Assume the air temperature remains constant. So yeah, it's a changing state, right? You have a certain pressure and volume that in your lung, and then you increase the volume of the lung. That means the air inside the lung will have a greater volume now. The pressure has to change. This is just applying the, this is a constant according to the ideal gas law. This is a constant. You are going from initial to final. Initial 1, final is 2, so 1 to 2. And this is, there is the same amount of air. So the N is the same. There is no change in the N. And also the question says temperature remain constant. So T1 is equal to T2. It reduces to Boyle's law. Now we can plug into this equation and find the new pressure. P1 is given, V1 is given. V2 is given, but P2 is not given. The question is, find the new pressure. Substitute and get the answer. So you can do a simple algebra again. Okay. So here P1 and P2 is up and down. right? And it is not temperature. So if you put the P1 and P2 in the same unit, that's okay, because a matter of multiplying by a factor, not for temperature. For temperature, adding, right? So since it's not a temperature, you can put both of them in the same unit, whatever the unit it is given. I'm sorry, I did V2 is not the unknown, right? What is the unknown? V2. Yeah. So this is not what I should be doing. I have to make the P2 as the subject. So P2 is equal to V1 divided by V2 multiplied by P1. That's good. If you don't like this algebra, you can write just the whole equation in the calculator with the equal sign and ask the calculator to solve for the unknown. Okay. Here it's not a difficult one. V1 and V2 can be in the same unit. You don't have to convert it into meter cube. So what is initial volume? 1,300. What is the final volume? 1,300 plus 450. Multiply by initial pressure. Initial pressure is 1 atmosphere. Can I put it in atmosphere? Yeah. Then what happened? P2 will come in atmosphere. The answers are in atmosphere. So don't waste your time in conversion. All right. Only when it is temperature, you have to be careful. So it will be faster. So you should get this answer. Please check. Number 11. A diver observes an air bubble of volume 1 centimeter cube rising from the bottom of a lake, where the absolute pressure is 2.50 atmosphere, to the surface, where the pressure is 1 atmosphere. So I would like to draw a picture so everything is clear. You don't have to keep reading this again and again. So bottom is initial. So let's say 1. Surface of the lake is 2, or the ocean is 2. So here you have a P1, V1, and T1. Here you have a P2, V2. For the what? Not for the ocean. For a bubble that start from the bottom of the ocean and come to the top of the ocean. So this bubble, which is an air bubble, so we are looking at the gas, which is the air. Okay. So we are going to assume that bubble obeys ideal gas law. And then we will apply the equation, which is the most general form. You cannot go wrong when you write this. When you write this, you cannot go wrong. Okay, this is always correct because you know this is equal to a constant, which is the R. Hope you are getting the point. Okay, this is also R, this is also R if it is an ideal gas. But you are looking at an amount of air which is trapped in that bubble. That means N1 is the same as N1 is the same as N2, same amount of air. And we are also going to, is there any other assumption? No. The question says the temperature is not constant. So I cannot cancel the T1 and T2. So you have to be careful to read the question, not make any assumption. Any same thing, it must come from the question. N1 is equal to N2 is obvious because the same bubble, same amount of air, when it comes up, it will be the same. There is no leaking. All you have to do is to substitute. I believe, let me go one by one. What is this? This is V1 at the bottom of the lake. And this is P1, the bottom of the lake. Initially, at the bottom of the lake, they are bubble. To the surface is the number 2. So this is P2. And this is T. Okay, I'll use small t just to be careful because it is in Celsius. So I will remind myself you should not substitute it right away. Excuse me, guys. If you keep talking, I will send you outside the class. If you have a question, raise your hand. Don't talk to each other and pay attention. And what is this? That will be T2. I will use the small letter t. So I'll remind myself it is not in Kelvin, it is in other than Kelvin. Right. So all you have to do is to substitute the values into this equation. P1 is given, V1 is given, T1 is given. What is it given? What is the question? Reaches the surface. Same temperature. What is the volume? So, yeah, why did I put 2? So, P2 is not given. V2 is given. Is it given? That is the unknown. Okay, right. P2 is given. V2 is not given. T2 is given. So, this equation it has only one unknown. So let me take my calculator out. You can of course move it around, but anyway, why not use the calculator? So my calculator is here. I will substitute. Now help me. We will do this. So the fraction. P1. It is in atmosphere. Do I need to convert to SI unit? No need, because you have the P1 and P2 both sides, right? So it is no use converting it because whatever the conversion factor will appear in both sides of the equation, they are going to cancel. It is not temperature, okay? You cannot do that to temperature. Temperature is not a factor, it is a subtraction or addition. So P1 is equal to 1 atmosphere multiplied by V1 is equal to 1. Again the same thing. It is in centimeter cube. I don't bother. Oh, I'm sorry, yeah. Bottom, right? Bottom of the ocean. It is 2.5. Thank you. Good, thank you. Multiply by keep in your mind 1 is the initial is at the bottom of the ocean, so it's 2.5. Thank you. And multiply by V1. V1 is 1. Do I need to convert that to meter cube? We better not, because the answers are in centimeter cube. So if you put that in V1 in centimeter cube, you'll get the answer V2 also in centimeter cube. So go down. T1. Now we have to be careful. At the bottom of the ocean, the temperature is, I don't say 4 degrees. Yeah, it's cool there. But it must be in, there is no choice here. Excuse me, please. Please keep quiet, please. You have a question, ask me. I'm going to put that in a bracket. So 4 Celsius must be converted to, better to put this 0.15 as well, just in case, okay, so you don't do too many rounding. Right, that's fine. So I got the left-hand side. You bring this guy up. Now you write the sign, equal sign, not the operation. Alpha, calc. Where is the calc? Yeah, here, okay. Right. Then the fraction, again. The right-hand side, P2, which is 1 atmosphere, multiplied by V2, unknown. That's what we need to find. That's the question. What is the, yeah. To convert the pressure to Pascal. No need. Why? See, 2.5 is P1, right? P2 is 1. If you want to convert, what will you do? You will be multiplied by a certain factor. that factor going to be on the left-hand side as well as the right-hand side. They are going to cancel. You are just wasting your time. Okay, time is of importance when you are doing the exam. Yeah, if it is appearing in both sides as a ratio in the same side as a ratio and the either side as the same level, then you don't have to worry about converting it. Okay, but you cannot do this for temperature in Kelvin. Okay, you have no choice there. Okay, except for temperature, you can do this trick. It will save you time. Right. Now, volume is the unknown. Now, I put the initial volume in centimeter cube, 1 centimeter cube. And I didn't bother to convert it to meter cube. Why? The answers, because the question is to find the final volume in centimeter cube. So it is wiser to keep it in centimeter cube. So you will get the x in, this is the unknown, also in centimeter cube. Now come down, what is this? Temperature. Temperature at the bottom of the ocean is, but at the surface is 2. How much is that? 23 degrees. So you must convert to Celsius, 23 Celsius. So you must convert that 23 Celsius to this. You have no choice. It must be in Kelvin. Okay. No, that's it. We have done everything. This is the best way to do this question. Use your calculator in the equation solving mode. Now you will get the x in centimeter cube. Shift calc. This is not the answer. You have to be careful. You should see x equal to something and the L minus R and blah. It comes in the second step. You have to press the operation equal. There it is, 2.67. That's the answer, right? Here it is. Yeah.
So when we were putting all the information in the calculator, would it be fine if we just immediately plug in the temperature in Kelvin instead of doing Celsius, doing conversion?
Yeah, then you have to go. No, if it is given in Kelvin, it is not given in Kelvin. You want to put them in Celsius because both sides is.
No, what I'm saying is, so we have them in Celsius, and we know we have to at the end calculate the operations unless they're. So can we just put the final Kelvin in product? So instead of doing 2 or 4 degrees plus 270,
okay.
Put final product.
Okay, tell me what are you going to put? What are you going to do differently here? Let me again go back to the equation. This is the equation. What are you suggesting to me? Are you going to put 4 here instead of 4 plus 273.1? You separately do the calculation in a calculator and write it.
Can't we just do that instead?
You think that is easier?
No, I'm saying just doing instead of putting brackets 4 plus 2.
Yeah, you are saying okay, you do it in your mind. In your mind, so it is 277.15. Okay. Yeah, you can do that. What's the difference? Nothing. Okay. All right. You can do that. Yes. Yeah. All right. So what he is suggesting here, this 4 plan, we do it in your mind. 273.15 plus 4 is 277.15. Okay. No problem. Okay. Right. So let's go to the next one. Question number 12. An ideal gas is initially at temperature 300 Kelvin, volume 1.5 meter cube, and pressure 2 into the power 4 Pascal. What will its final temperature be if it is compressed to a volume of 0.? So it's also a state-to-state question. So all you have to do is to just blindly write this. You don't have to think anything, because this is always true. 1 is for initial, 2 is for final. And just because this is equal to R, right? It's a constant, no matter what, if you can assume ideal gas behavior. Right. Now, what is this? Initially, so this is T1. It is not small t, it's a capital T, so it's in Kelvin. And this is V1 in meter cube. And this is P1. And what will be final temperature if the same amount of thing is compressed to a new volume? This is V2. And final pressure, this is the new pressure. So what is unknown is he's asking for T2, the temperature. What about this? Because there's no leaking of anything. It's the same amount of gas, so N1 is equal to N2. So it's the same story, right? We can use, these questions are actually easy. You can take your calculator and just substitute into this. There will be only one unknown and solve for the one unknown. So let me clear this. I will start with the fraction on the left-hand side. P1, somebody help me so I don't make a mistake. 2 into 10 to the power 4. 2, this one, 4. You know how to use that, right? Your calculator, 10 to the power is here. Multiply V1, 1.5. Everything in SI unit, so we make it easy for us. Come down. Temperature is also SI unit, 300. And you bring it up, put the equal sign, then fraction again, P2. Is that the question? No. Temperature. 8? Where is 8? Last part, okay. 8 10 to the power 4. Multiply V2, 0.7. And come down, that's the unknown. Question X. Shift, not shift. Alpha? Okay. Right, that's it. Just make sure you didn't make any mistake in your equation, then ask the calculator to solve it for you. This is not the answer, you know it is from. You have to press the equal button again. You should see this x equal to and L minus R equal to 0, then it has done the. So the answer is correct, right? Okay. Right, we can go to the next question. Number 13. This is a statement question. We learned this in chapter 8, maybe probably the last slide. Ideal gas the average kinetic energy of the gas molecule, you know, the average kinetic energy is actually the internal energy, the U, that we proved at the end. It's the volume of the given amount of ideal gas increases at constant pressure. The average kinetic energy of the gas molecule will what happened to the kinetic energy when the volume of ideal gas increases at constant pressure. Constant pressure means, you know, what is this ideal gas law is this. Pressure is constant. When the volume increases, these are all constant. What will happen to the temperature? Increases. So here volume increases mean its temperature will increase. And you know, when the temperature increases, the energy will increase. So that's why the answer is A. So you need to remember that the kinetic energy is the, for an ideal gas, the kinetic energy is the only energy. So the energy, if you remember this expression, the energy is for an ideal gas is only depend on the temperature. So when the volume increases, temperature increases, therefore the energy will increase. None of the other answers are correct. Number 14. And that is the same story, right? Internal energy of an ideal gas depends only on the temperature of the gas, not on the pressure or volume. It looks a bit contradicting because in the previous question, the volume is which is increasing. But the volume increase results in a temperature increase. Therefore, the kinetic energy will increase. Number 15. A gas expands from initial volume of 4 liter to a final volume of 6 liter at constant pressure of 100 kilopascal. So now we are coming to chapter 9, the thermodynamic processes. the the work done and so on. Right. Constant pressure, the work done is given by this equation. You don't need to get to area or anything. This equation is valid for constant pressure. Only for constant pressure. The work done on the gas is given by this equation. So you just substitute. P is 100 kilopascal, right? Kilopascal, and well, let me do this. You have to convert that to Pascal. SI unit is Pascal. Pressure SI unit is Pascal. And the change in the volume, 4 liter, it becomes 6 liter. So the change in the volume is 6 minus 4, which is 2 liters. But liter must be converted to meter cube. So how do you convert the liter to meter cube? You multiply by or divide by 1000. Okay. Liter mean a small amount, right? You know, 1 liter bottle. Meter cube mean, imagine a something, a container 1 meter by 1 meter by 1 meter. It's like quite big. So you can fill thousands of these 1 liter bottle into a 1 meter cube. Right. But you know, you see something. This will cancel with this. You become 1, right? So, in other words, kilopascal into liter is also joule. Like Pascal into meter cube is also joule. If you know this trick, you know, you don't worry about converting. One is kilopascal, the other one is liter. If you multiply them, it will be SI unit joule.
Given any other,
not any other.
it's given any other, we can't.
We have to convert. We have to convert. Okay. Here also we are actually converting, but you know, we found a shortcut because you are multiplying from kilopascal to pascal by 1000. From liter to meter cube, we are dividing by 1000. So why bother? You just kilopascal into liter will give you the answer in joule. What's the answer? You get 200, right? 2 into 100 will be 200, but there's a negative sign, so it will be the answer. Yeah. 10 to the minus 3, because liter is not SI unit. Meter cube is the SI unit. Kilopascal is not SI unit. Pascal is the SI unit. No, only here, right? Suppose the question give the pressure and the volume in kilopascal and liter, don't bother, you just multiply. But you have to keep in mind, kilopascal is not SI unit, liter is not SI unit, but we don't care, the product is SI unit. Okay. The actual SI unit is Pascal and meter cube. Number 16. A fixed mass of gas initially occupies a volume of 2 liter at a pressure of 3. So now here again, this is kilopascal, this is liter. Are they SI unit? No. But if the question is to find the work done or the area or whatever, we don't care, because we have to multiply the kilopascal with liter. It will be in joule. So there is nothing to, don't need to bother to convert them. Just keep them in kilopascal, keep them in liter. the product will be SI unit. Right, what do we do now? Question is the work done on the gas. Okay, so is this, can I use this equation? This equation is used only when the pressure is constant. Is the pressure constant here? No, it is varying. But we have a trick. We cannot use this, but I know that the work done will be area under the graph, absolute value of the work done. Okay, I shouldn't say work done. Absolute value of the work done is area under the graph. So I can find this area. There are two ways to do that. You know, if you know it is a trapezium, for a trapezium it is half P1, P2. Right? And this, the height of the trapezium, well, it is the distance between the two parallel sides, which is delta V. Okay, that's one way of finding the area. Or you can say, I find this area separately, a triangle, and I find this area separately, a rectangle, it will be the same. I can also say it is equal to half. You know how to find the triangle area? Half into this one, this H, which will be P2 minus P1, multiplied by this log, delta V, plus, that is the area of the triangle, plus the area of this rectangle, which will be P1 delta V. One can show these both are the same. Okay, one can show they are the same. This kind of, you know, there is a easy to remember. What is this? The average pressure, right? Initial pressure, final pressure, divide by 2. Average pressure multiplied by the change in the volume. Anyway, shall we do it? Okay, let me use this because it's quicker. Half absolute value. We don't know. I mean, just to get the positive value. P1 is 3. P2 is 8. And delta V is, how much is this here? Oops. 8, right? Here, 2. 6. Right. This is 4. This is 11. 4 into 11 is 44. 44 divided by, am I getting it wrong? 8 plus 3 plus 3. 8 plus 3 is 11. 11 into 6, 66. 66 divided by 2 is 33. Yeah, I did not. Right. So the answer is correct, but that is the absolute value. Don't be in a hurry. Did we get the work done? No. We only got the absolute value of the work done. How do I know whether to put a positive sign or negative sign? If it is an expansion, if final volume is greater than the initial volume, so the arrow is this way, right? This is the initial and that is the final. So it is a expansion mean it's negative. So that's why D is the correct answer. Number 17, statement question. When the first law of thermodynamics is written like that for a closed system, which of the following statements is false? When you write it like that, this is the increase, okay, change in the internal energy mean final minus initial, that mean increase. Okay, it can be positive, negative, that's a different story. This is the increase in the internal energy. Q is the heat into the system, right? The definition is he is flowing into the system. And W is the work done on the system. So let me read one by one. Which is false? Okay, he's asking which is false. A, Q is the heat flowing into the system. Is it correct? Yes. But because it is correct, it is out. Because you have to pick the one which is incorrect. Yeah, false. So he is out. B, W is the work done on the system. That is also correct. So it is out. C, when no heat flows in or out of the system, what does it mean? Q is equal to 0. Not going. So Q is equal to 0. And a positive work is done on the system, that means W is positive. The internal energy of the system increases. W is positive mean Q is 0, that means delta U is positive. Positive mean increases. That's correct. So he is also out. D, when the heat flows into the system, that means Q is positive. And no work is done, W is equal to 0. Delta U is again positive. So it is also correct. Therefore, he is out. W is positive when the system does positive work. System, not on the system. The system itself is doing the work, mean work done on the system is negative. So it is wrong. Therefore, we pick it. I don't, this is confusing. All right, let me not do anything. So this is the one that is wrong. Therefore, I select it. A gas gains 600 joule of heat and does. Who is doing it? Gas, the system, right? And the gas gain mean heat is flowing into the system. So what is this? This is Q and it is positive. And gas is doing, does 100 joule, then when W is equal to 100. What is delta U? That's the question. Q is Q plus W. Q is equal to plus. And W is equal to minus 100. Okay, so yeah. He has to tell us from the statement. The gas does 100 joule of work. Does mean the present tense of doing, right? I mean the gas. Who is the system? The gas is the system. So the work is done by the system. There is some work is being done. It is the gas is expanding. If you look at our model system, the gas is pushing the piston out. So gas is doing the work. Not you are doing the work on the gas. So the amount of work is 100 joule, but it is done by the gas, not on the gas. Then it is, So question is, W mean work done on the gas. But its value is, we should put, because really you are not doing the work on the gas is doing the work. So W, the work done on the gas is equal to negative 100. Okay. Number 19. 60 kilogram man climbs stairs to reach the top floor of a building. A total change of height of 100 meter. So he's climbing 100 meter vertically, height, okay? So that's what we need for the potential energy. As a result, he uses up 21 calories of stored food energy. How much heat must his body dissipate? So this person is, I mean, you probably in your formula sheet, you will see that formula, which is delta U is equal to is this, but you say that there is no W, and the Q is taken as change in the internal energy, the thermal energy, 0. So this internal energy now will come from not only the kinetic energy, there is no kinetic energy change anyway, there is a potential energy change and other forms of energy. So this is in the formula sheet, okay. Now use this to answer the question. What he is asking, this change in the thermal energy. So you substitute, there is, he is no change in the kinetic energy because he is not running or speeding or anything. He is just slowly climbing the steps. So you can say always he has a 0 speed. So no change in the kinetic energy. There is a change in the potential energy, which is mg, the height delta y. And you're using up the food energy, so it is decreasing, right? The food energy, it is releasing the energy, so minus 21 calorie, right? So you have to convert it into joule, negative sign. Plus the change in the thermal energy equal to 0. So when you do that, you will get a negative value for the delta thermal, it should be. So the answer will be this, please check it, 29 kilojoule. You have to be careful with the units, right? Probably you will put everything in SI unit, you will get the answer like 29,000 joule, which is 29 kilojoule. Question number 20. 2 moles of an ideal monoatomic gas initially at a temperature of 300 Kelvin. If the gas gains 2,800 joule of heat and does 400 joule of work, what is the final temperature? Right. It's a combination of the first law of thermodynamics and another step. So let me write the first law of thermodynamics. Q is given. Is it positive or negative? Positive, because it is gains, right? So the heat is going into the gas. And W, yeah, who is doing the work? Gas itself. So negative 400. So you'll get the delta U, but that's not the question. The question is, what is the final temperature? What is this equal to? 2,400 joule. For an ideal gas, U is equal to ideal monoatomic gas. U is equal to, it's in the formula sheet, 3/2, I hope I'm not making a mistake, RT. That's nRT, I think, yeah. Can you please someone check that, please? 3/2 or 2/3? Right, let me go to 3/2, correct? Okay. So that means delta U is equal to what? Delta U will be, the only thing that changes is the temperature. So now I can write here for delta U 3/2, N is 2 moles, R is equal to 8.314, and delta T is final temperature, which is unknown, minus initial temperature, which is 300 Kelvin. equal to 2400 joule. So everything in SI unit, the only unknown is the final temperature. Somebody do it for me and get the answer. See whether you are getting the right answer. Can you do someone, please? I just want to be sure I didn't make it. Since all in Kelvin, the answer should be in Kelvin. All right, let me do it. I cancel the 2 and 2, so 3 multiplied by 8.314 multiplied by, I'll call x for the unknown, minus 300, close it, put the equal sign, equal to 2400. Solve it. Shift, calc. Yeah. Okay, 396. Number 21. A gas enclosed in a container filled with a piston by doing 190 joule of work on the gas during a constant pressure process. If the internal energy of the gas increases by 80 joule, then it's also a combination of what do you call thermodynamic processes. We have to pay attention to what kind of pressure is this? Constant pressure process. Right. When the pressure is constant, I know several equations. One of them is this. It's all there in the formula sheet, grouped by the process. So you know which equations to pick, okay, in the formula sheet. Will it help us to solve? No, we may need the first law of thermodynamics, which is this. So which we have this, right? It's given here. By doing on the gas, so it is positive. So I can substitute that. If the internal energy of the gas increases by 80 joule, so this is delta, internal energy, delta U is equal to 80 joule. Right. The question is about heat, right? So we can find the heat. We don't even need this. I thought it will be how much? Minus, right? Okay, now you know the answer. Easy one. The last one. A graph is shown where 0.653 moles of ideal gas that undergoes the cyclic process. So start from A, it goes to B in this direction, then B to C in this direction, and C to A. So it's a cyclic process. Start from A and go around and come back to the same place counterclockwise, right? This is in a PV diagram. P in the vertical axis and volume. Excuse me, please. And the question is, what is the work done on the system in this cyclic process? There's a shortcut here. The shortcut is to remember, in a cyclic process, the work done will be simply the area enclosed by the cycle. All you have to do is to get this area. But do you know how to get this area? It's a curve, right? So it's not a triangle. Can you say it's a triangle? No. So I cannot use that. But however, you can go one by one. It will be this area if I use this line. That is the work done in this. This is what kind of process is that? It is a isothermal. That process is isothermal. So I can say the total work will be work done from A to B plus work done from B to C plus the work done from C to A. This is easy. What is the answer for C to A? 0. Because it's a vertical line. It is covering any area? No. It is, in other words, it is a constant volume process. When the volume is constant, work done is 0. The piston is not moving either side. So this is 0. This one, that is this guy, right? If I use another color, this area. That's easy. Tell me. It's expansion, so it is negative. The area will be 220 multiplied by 23 minus 11. I hope I'm not making a mistake. Please correct me. I'm getting the numbers right. This is 220, right? It's kilopascal? Yeah. So I don't need to do any changes. And this is liters, right? Yes. So 23 minus 11. That is this one. Right. Now let me come to the isothermal process. How do you find the work done for an isothermal process? There's a formula. It's in the formula sheet. Okay. For an isothermal process, the work done is nRT ln. Okay, so we just substitute. Okay, here, we are not looking at the area. We have an equation. Okay, so we just have to substitute the values into the equation. WBC. N is how much? 0.653. R is 8.14. T is, it must be in Kelvin, 932. Ln, V final is, is a ratio. Do I need to convert them? No. As long as you put them in the same unit. Final volume is 23, initial volume is 11. Just calculate this, you will get the answer. You will get 1100 joules, something rounded to, then it will be kilojoule, it will be 1.1 kilo.
How would we put N in the calculator?
Yeah, let me do this in the calculator, okay? Right, let's do it in the calculator.
Also, in the formula sheet, there's a negative for the N. And
No, there's no there is negative? Oh, I'm sorry. Oh, I forgot that. Yeah, thank you for, I thought yes, there is a negative sign. Okay, there is a negative sign. Actually, I should have known. Yeah, it's not the area now. We are going. See, I made a mistake here. Eventually, the whole thing. What is the mistake here? Final volume is because you are going in this direction from B to C. Final volume is 11. And see, there are so many things you may miss. That's why you have to be very alert when you do that. You are going from B to C, right? So the final volume is 11. So that is a matter of change in the sign here. So this ln of a value less than the 2.7, the value ln of E, right? This will be a negative quantity, and there is already a negative. Negative will make it. He corrected me. There is a negative. So negative will make the whole thing positive. You should have known that, because it's a isothermal compression. Compression, the work done must be positive. So let's do it in the calculator. Right, let me clear everything. So this is not a solving, but you will use the expression and press the equal button. Negative, I will use this negative. 220 multiply 23 minus 11, like you suggested. I'm not good at mental math, so I better do the whole thing, okay? I don't want to make mistake. I don't want to take a chance. So 23 subtract 11. Good. So don't tell me, suggest anything. I'm not going to do any mental math. I will just do it. Right. Yeah, not that. 23 minus 10 is how much? 13. So 13 minus 1, 12. You could have written 12. Minus 0.653 multiply 8.14 multiply 932 multiply. This is, where do I get this in the calculator? It is ln, right? Natural log, this guy, ln. Okay, and put the fraction. 11 come down 23. You have no excuse to tell, sorry, that's a mistake. Okay, let me delete it. We have to come up. Now close the bracket. You have no excuse to this long calculation, logarithm, and so on. Well, you're not doing anything. Only thing is to know how to enter the values in the calculator. Then you press the equal button, you get the answer. I hope I get the right answer. I hope I didn't make any mistake. Please. Yeah. 1014 to two significant digit, it will be 1.1 10 to the power 3, which is 1.1 kilojoule. Oh, I'm not getting one. It's 1.0. I'm sorry. This is 1.0, right? Not 1.1. What is the mistake I made? Did I make any mistake? It's 460. N is equal to 0.220, 23 minus 11. That's correct. Then you have the minus 0.653. That is correct. 8.14. That is correct. 932 Kelvin. That is correct. Lin. I don't know. I haven't done anything wrong. So that means question answers are wrong. When you round it to two significant digits, what's the answer? 1,100. 1,000. 1,000, not 1,100.
Don't take a question like
No, come on, it's a calculator. There's a mistake in the calculation, probably mistake in the question itself. It is 1 point. I'm a bit worried. Why did I make a mistake? I don't think so. Did I make a mistake in the R value? What is the R value? 8.14 or 8.314? Right. Okay, come on, guys. You should have corrected me. Right. Now I'm so happy. Did I put the one? Yes. Okay. Right. Alhamdulillah.